Tonight's the night, huh? First midterm. We'll be fine. Make sure you pencil in your student ID properly and your name. And you also have to sign the question sheet. There will be no questions from the lab. And everything that I talked today about, most of it will not be part of that midterm. That will be in the next midterm, except the stuff that you know already, which I also talk about. Otherwise, you wouldn't understand the stuff I don't talk about. I want to talk about. Too much talking about. Okay, so when we look at stars, people tell us what kind of stuff is there, what kind of elements they are made of. And how do we know that? Yeah, we take a spectrum. Because we know that if you have an atom, has electrons, and I excite an electron from a lower into a higher level, and it goes back down to a lower level, it emits photons, it emits light. And light travels infinite distances. It just takes a little while, okay, or a long while. And so you can pick up that light, and then put it through an analyzer to a spectrograph, a very sophisticated spectrograph, and you get a line spectrum, like you see here on the left side. This is the line spectrum of solar line, and this is in wave numbers here. This is the different regions here. And what kind of elements do we have in the sun? Hydrogen and helium. So this is actually the solar spectrum of hydrogen here. Huge spectrum of hydrogen are different. So this is wave numbers. So yeah, they all, that goes from here to here, and then this one goes here, and this one goes here, and so on, and this one goes here. So you have it all, the whole spectrum. So it's just chopped up here. And so there's helium and hydrogen. So how do the elements, how are they made? They're made through synthesis, yeah? Okay, stellar synthesis. And so you know, if you have one element and another element, you just cannot put them in the bottle and shake them, and then they make a new element. That would be great if that would happen. Why can't you just take the two elements and put them together and make a new element? What's the problem? The problem is that you have a positive charged nucleus. The electrons also, you heat them up, you heat it to high temperatures, the electrons don't go away. Okay, you ionize it. And so now you have these nuclei, and they need to fuse, they need to get together and make a new nucleus that is heavier than the individual ones where it came from. Ideally, it will be the protons and neutrons, the sum of both of them. That's usually not the case, but you can be happy to get the protons together, okay? So the problem is that this is positively charged, and so they repel each other. And so you cannot really make this here on the desktop. You need to have high energies. So we heat this up to very high energies, to high temperatures. See, I'm substituting energy and temperature with each other, and we will learn about this. You heat this up to high temperature, so they have very high kinetic energy, and then they can move so fast that they come very close to each other, and then there is something called the strong force. The strong force only has a very short distance reach. It then can reach it and hold them together. That's what holds the nucleus together. Remember, we talked about the strong force when we see the protons are held together in the nucleus. They're also positive. So you have to overcome this strong force, and you can do this only at high temperature. That's what happens in the sun. We have this very high temperature, and a hydrogen atom and another hydrogen atom come together and they make what? Helium. And if you have hydrogen and helium, it makes the next higher one. And so you can't make a whole lot of heavy elements in the sun, but you have some a little higher. And this is called fusion. And this is what we're trying to do on Earth here with big lasers to bring these, what we call a plasma, so close together that it starts fusing, and then it's a continuous reaction that we sustain. This reaction was sustained when I was your age about, it was 10 to the minus 18 seconds. That's how long they could sustain it now. Now they are already close to a second. And this was then, they said then it's about 30 years out, 30 to 40 years out that we have fusion energy. Now, you need to have weeks and years to sustain it to use it as energy. So if they say we are 30 years out, that might be again right, at least 30 years, okay? But we should not give up on it. So this is what happens in the sun. Now remember, we had this mercury vapor lamp. And the vapor lamp, if you wouldn't know that it's mercury, you take it and vaporize it, and then take a spectrum of it, an emission spectrum. And you see these three lines that I projected here, put to a grating and projected on the screen here. And these lines are specific for mercury. These are the three energies. There's no other atom that can have these three lines by itself. Okay, there are other atoms that can have, but they have also other lines. And so with this spectral analysis, you can say what you have. Now, in order to make us, here we have carbon and hydrogen and oxygen. Hydrogen is easy. Oxygen and nitrogen, these are already pretty heavy elements. You need to have much bigger suns. And these bigger suns are called supernovae. And there you can synthesize our carbon. We're made out of carbon and oxygen and hydrogen and nitrogen. That's about it. Okay. And so this must have come, as the Earth was formed, from outer suns. There are about 100 billion suns in our galaxy. 100 billion. Okay. And how many galaxies are there about? There are about 100 billion galaxies. Pretty hard work for one person to create this all. Okay. But this is just a side note. Okay. So as you look at yourself, or if you look at ourselves, we're nothing but stardust, okay? Carbon, and hydrogen, and oxygen, and nitrogen, we're just sprinkles of stardust, okay? So look at this when you are very distraught. That might help you putting things in perspective, okay? So if you have silver and gold and these heavy elements, you really need huge supernovae to do that. And this happened, actually. And that's why these elements we have here on Earth. That's why we have iron and so on. Okay, so just as an application of the spectral stuff, you looked at, in the lab, you looked at sunscreen, and you could see that they are cheating on you, these guys who make the sunscreen. They put some stuff in there, and they say, put a big label on there and sell this for exorbitant prices. And actually, much of the stuff, many of these sunscreens are not very well, working very well. They don't absorb the light as much as you think it would. So they print an SB50, and then you find out it's only an SB10 or something. But you pay big buckaroonies for this. All right, so today we're going to talk a little bit more about the one-electron systems, and then we're going to go to the more interesting system. That's the periodic table. We don't have one-electron system. Each element beyond hydrogen is more than a one-electron system. And we see how these electrons affect each other energetically. So you have learned now, if we have these three quantum numbers, n is the energy, L is the shape, and m sub L is the orientation in space. So we have seen there is in 1s for n equals 1, for n equals 2, there's can L equals 0, and L equals 1. So we have 2s, 1 2s orbital, and 3 2p orbitals in all three directions. And then for 3s, we have L equals 2, so we have 0, 1, and 2. N equals 2, L equals 0, 1, and 2. If it's 0, it's a 3s. If it's 1, it's 3p, so we have 3. If it's 2, it's 3d. We have done this ad infinitum, as we say in English, till the cows come home. Okay? And so you see, and for one electron, it can go either here, or I give it energy, it can go here, or it can be here, or it can be here, or it can be here. If I give it more energy, then it can be here, 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 or here. So these are all the same energy for one electron system. They are degenerate. That means degenerate of the same energy. In truth, they are not really degenerate. There are some differences, energetic differences within the same main quantum number. And this is what we're going to talk about today. So if you have a multiple electron system, so you have the 1s, L equals 0, all right, this would be this here. And then you have the 2s, the 3s, the 4s. The 2s, you have 1 node. The 3s, you have 2 nodes. The 4s, and so on, you have 3 nodes. And if L equals 1, you have p electrons. We can have 2p. 3p, 4p, and so on. And now I need to demonstrate something to you. We need a demonstration, okay? Let's see. I need some help. Why can you be my nucleus, please? And I need you, and you, and you, please. If you could help me, you are electrons. The nucleus is the smallest, it's in the middle, okay? But most powerful, attraction. It's positively charged, and we have one electron. If you could stand aside here, you are, so just here that you're not in the nucleus. The nucleus doesn't see you yet, just ignore the nucleus, okay? So we have a one electron system. So this nucleus is positive, and you are what? Negative. Negatively charged. What's your name? Kyle. Kyle is negative, and what's your name? And Stephanie. So Kyle is attracted to the nucleus, because there's Coulomb interaction. So Kyle has the undivided attention of Stephanie, of the nucleus, okay? Along comes, what's your name? Charles. You know, yeah, Charles. Along comes Charles and says, no, we are helium. I have 2 electrons. I want to be also there, okay? I want to be also there. So where would Charles position himself the best? Where would you go, Charles? He's negative and you're negative. You think that's going to work out? Okay. Now, she's positive, negative. You're very close to him. Don't you want to go away from him as far as you can? Aha, go a little bit over there. So now Stephanie is seen by both of them. So she has to divide her attention. So she pulls on him, or he pulls on her, she pulls on him, and on him about equally, okay? So this is okay. But it's not as, if he would be alone, then he would only experience her at pull. But now she has to divide it between the two. Now, what's your name? Ben? So there comes Ben. He says, I want to be part of that mix, okay? And Ben says, okay, I'm going to go into the next higher quantum number, because n equals 1 is already full now, okay? Go to the next, so he goes into 2s or 2p or somewhere. So now, can you turn towards your nucleus, please? Now, do you see that nucleus very well, Stephanie? Do you see him well? No. Okay. So do you see him well? So your attraction towards him is the least, isn't it? Because he's hiding behind him here. And so if I want to ionize him, then I take energy, and he is pretty far out. The door is my infinite level. So I take him here, the energy, and now I have him ionized, okay? So now this is a plus, okay? So now the next one, these next ones would be equally easy to ionize, but more difficult than Ben, okay? So there's the shielding effect. So if you have more electrons outside, they are shielded by the inner electrons. So they don't experience that attraction from the nucleus as much, so they are easier to ionize. Ionizing means that the electron is removed from the atom. So that's the ionization energy, the energy that you need. Remember, we have these energies. This was a negative level, negative, and this was negative. So the overall level is 0 here. So you need that energy positive. You put it in to get it to 0, and he's out the door. All right, did you get that? Thank you very much, Adamson. Okay, now you see, this is the shielding effect you have here. The 2s is a little bit lower. Of course, it's not a whole quantum level, but it's a little bit lower in energy than the 2p's. There's the px, the py, pc, they are on the same level then, okay? And of course, there's also that node in there. The 2p has a node, and so that can't be that gets as close to the nucleus. Yeah, also, that's also a limitation. So the 3s is lower than the 3p, and the 4s is lower than the 4p. And now look at this. If you come to quantum level 3, that means n equals 4. The 3d, if you go across here, this is our energy, you go across here, the 3d is a little bit higher than even the 4s, all right? And this is where the transitions come in, the transition metals. All right, but you don't need to know this yet. So we talked about the energy of the 2p is a little bit larger. The 2p is a little bit larger of the 2s. And the energy of the 3d is a tiny little bit larger of the 4s. So the 3d, actually, even if it's in the third quantum level, it's a little bit higher in energy than the 4s. This you cannot memorize. You need to sort of deduce that. I mean, we'll get the hang of this. Now let's talk about these one electron systems again. You know now what ionization energy is, and that you leave an ion behind. If I have a electron removed, it's a cation, it's positively charged. Now, remember, for the one electron system, this was the energy, and this is the energy of that level is exactly the ionization energy that you need to remove it. Because that level has the energy, so in order to remove it, I need to put up the energy with the opposite sign. Okay? Now that was Z squared divided by n squared times this is an energy, the Rydberg constant, and Z was in a one electron system. Here in hydrogen it was 1, and the n depends 1, 2, 3, and so on squared. All right? Now, if you have helium, a one electron system, helium is a one electron system, but Z or Z is not 1, it's 2. So the ionization energy is then 2 squared divided by n squared, that would be 1, and C squared would be 4, divided by second level would be 2 squared would be 4. So what you get is, you get it to completely remove a hydrogen, and you measure these ionization energies. To completely remove a hydrogen, you need now energy per mole. So we already calculate this only for 1 electron, but you usually have a mole of substance or a mole of electrons. So you multiply this with this number here with Avogadro's constant, and you have it for 1 mole. And this would be 1312 kilojoules per mole. But this one here, for helium to totally ionize, would be 5,248. So that's exactly 4 times as much. It makes sense because the nucleus hangs on much stronger to it. So you need 4 times as much energy because you have this relationship here. Now, if we put that helium, now we have a helium atom. We have it in 1s2. So in the 1s level, we have 2 in there. Okay, and we want to remove 1. So how much energy would we need now? That's a difficult issue. So, and I want to remove 1, so this would be squared, but this is not in a 1 electron system. We're in trouble now. Okay, so you square that is 4, but that only is for 1 electron system. Let's see if I have some for many electron system. You have the effective charge here. That's what I just showed you here. That shielding is the effective charge, and so this effective charge you can measure through the ionization energy if you know the level. And now the effective charge would be then in this case would be about twice, not quite twice as much to remove that 1 electron compared to the 1 electron system, because the nucleus can't pull quite as much on it anymore because of that other electron that is there. So it has to hang on to both electrons. So it has to divide its binding strength to the electrons. And with this, the energy that you need to remove is smaller than when you had it before. That the helium nucleus is only binding 1 electron. You got this? Okay. So. And then you can have a helium, a 1s1 and a 2p1. You can put these electrons any way you want. This is not a ground state configuration. You have 1 electron in the n equals 1, and 1 electron in p equals 1. So 1 is in the second level, and this is in the 2p. So which one would be easier? Would it be more or less energy if you have one even higher up there? Okay, let's see. That would be less energy. That would be something like if you go from hydrogen, just in comparison, hydrogen to the continuum, it would be 328 kilojoules. You see this? I promoted it also already high in a higher level, and now one of this is in a ground level, but the other one is in an excited state. And so now I need less energy to remove it because I'm already closer to the door. You got it? Ionization energy. Okay, let's see if you got it. 1 second. So we have an atom or ion. So this is helium plus, is this a one electron system? Yeah, okay. Is this a one electron system? Okay, now so you can use that equation and just have C, not effective, C squared. You can calculate now which one has the lowest ionization energy. Okay, so why don't you do that and give me an answer and tell me which, I have only a one electron system, which one has the lowest ionization energy? What means I need the least energy to remove it. So we are here at the one electron system. You can just use your formula, actually, couldn't you? Did the DSP students get their notification now? Good. There were some of them, they were very close to the end of last week in the DSP advisor, and so we just got this morning, some of the stuff. That's a question for tonight, okay? That's a one electron system. But I don't know if this is on there or not. I really don't know. So, okay. So please follow me. What is set here? 1. Set here 2. Set here 3. Okay, you have 1 squared, 2 squared, or 3 squared, divided by 2 squared, divided by 3 squared, divided by 4 squared. This has nothing to do with chemistry, okay? Please discuss it with each other. Yeah, the smallest fraction is 1/4, isn't it? Okay. Yes. Wow, arithmetic. Good. Sort of. Let's do 24% and 1 joker. Okay. So these are all one electron systems. So what's for this here? This is C 1/4 R. Okay. What's that here? This is 4/9 R. Okay. What's that here? This is 9/16 R. Which one is the smallest number? Did you get this here at least? You get this, yeah? Okay. All right. So good. So now, which one is the smallest number? So this one is 0.25, then the other one is point something 44, and the other one is 0.56. So which one requires the least energy to remove? Okay, good. Right. So now you need to think. And now there's no formula. Think about the Super Bowl. Think about the blocking. They did blocking. So you have 1 here, 1 positive charge here, you have 2 positive charge here, you have 3 positive charge here. But they are blocked by how many? They are blocked here. So I'm asking you which is the lowest ionization energy. Which one is the outermost electron that you want to remove? Ionization energy always removes the outermost electron. So if you have a charge of 1, obviously there's no blocking. Okay. You have a charge of 2. How many electrons do you have? In this one here? Okay, there must be some blocking. Okay. And then you have a charge of 3, and there must be some blocking. So which one is the easiest to remove? Don't you think about this? Now we have shielding here, okay? I can line you up again and we make a demonstration of this.